Welcome back to the CCNA Cisco NetAcad Switching, Routing and Wireless Essential lecture series. If you are interested in the previous lectures, I will leave a link in the description for the playlist. Today, we will be focusing on module number 2, which is switching concepts. In this module, we will learn how the layer 2 switches forward data. We will cover frame forwarding and switching domains. Frame forwarding. Switching in networking. Two terms are associated with frames entering or leaving an interface. They are ingress and egress. Ingress is the entering interface, so where the data or the frame or packet being entered. And egress is the exiting interface, which is the frame or the data exiting port or the interface. The easy way to remember this is ingress is like input. It starts with IN, ingress, input. Therefore, it is the entering interface is the ingress interface. Egress is like an exit with an E, exit. So egress is the exiting interface. So that's how I remember for the exam. Ingress is the entering interface because it's like input, ingress, and egress is the exiting interface because it's like exit or egress, right? So with the E. So a switch forward based on the ingress interface and the destination MAC address. A switch uses its MAC address table to make the forwarding decisions. So when the switch receives the packet or the frame, switch forward based on the ingress interface and the destination MAC address, but the destination MAC address is learned through the MAC address table that the switch has. And also we have covered the fact that switch will never allow traffic to be forwarded out the interface it received the traffic in our previous lectures in Cisco NetAcad Introduction to Networks lecture series. Remember, when data is received, whatever the port, the interface which the data is received will not be used to forward that data out of it. So for example, if the ingress interface or entering interface is interface number 2, when that data gets forwarded, it will never be forwarded out of this port number 2. It will be forwarded either on 1, 3, 4, 5 or 6, one of those ports out. So that's how the egress interface will be selected, because the switch will never allow traffic to be forwarded out of the interface which the traffic is received. And the MAC address table look like this, where it associates the port number within the switch with a specific MAC address associated with that port. The switch MAC address table. So a switch will use the destination MAC address to determine the egress interface, as I mentioned before. However, before a switch can make this decision, it must learn what interface the destination is located. A switch builds a MAC address table to do that, and this MAC address table is also known as a CAM table or content addressable memory or CAM table. By recording the source, so what this table has is the recording of the source MAC address into the table along with the port it was received. So the whole purpose of a MAC address table or content addressable memory or CAM table is to assign the port with the associated with MAC address of the device that is connected to that particular port. The switch uses a two-step process when the switch wants to learn and forward the data. So in step 1, it learns, in other words, it examines the source address. It adds the source MAC if it is not in the table with that CAM table, and resets the timer out, setting back to 5 minutes if the source is in the table. So what it does is basically it go and look for that MAC address, and if it is not in the table, it's going to add that to its MAC address and reset the timeout setting back to 5 minutes if the source is already in the table. So if there is no MAC available, that particular MAC address, it's going to add to that table. But if there is MAC address already there, what it's going to do actually, oh yeah, I see that MAC address and associated port, and I'm going to reset the timer back 5 minutes. And the second step is to forward. So the switch will examine the destination address, and if the destination MAC address is in the MAC address table, it is forward out the specific port. However, if a destination MAC is not in the table, it is flooded out all interfaces except the one it was received. Remember, the ingress port is never be used for flooding out the data. So in that case, all other ports acting like egress or exiting interfaces, and it will just flood out all interfaces except the one which it was received. There's a video on your Cisco NetAcad called MAC address tables on connected switches. It's a really good video that cover all those topics. And if you do not have access to this particular video, I will post a copy of that video to my YouTube channel, and I will leave a link in the description so you can go ahead and watch it, as well as I will attach a card on the top right hand corner so that you can click on it and watch that video. I would recommend you are watching these complimentary videos to better understand the concepts that we are covering. Switch forwarding methods. Switches use software on application-specific integrated circuits, also known as ASIC, to make very quick decisions. A switch will use one of two methods to make forwarding decisions after its receiver frame: store and forward switching and cut-through switching. We briefly went over store and forward and cut-through switching in our previous lecture series, but in here we will go a little bit in depth how they work, and in labs we will learn how they actually behave. So in store and forward switching, the switch receives the entire frame and ensure the frame is valid. Then store and forward switching is method is used to transmit that data. The store and forward switching is the Cisco's preferred method of switching, and then cut through switching. Basically, how that works is forward the frame immediately after determining the destination MAC address of an incoming frame, and it knows the egress port. Just so as soon as they realize what egress, that the switch knows which egress port need to be used, and it just start to send the packet out without making sure the frame is valid. Store and forward switching. So in store and forward has two primary characteristics. They are error checking and buffering. Error checking is happening when the switch check the FCS or frame check sequence for CRC errors, and if there is a bad frames, the switch will discard that frame. Buffering, so how that works is the ingress interface will buffer the frame while it checks the FCS. This also allows the switch to adjust to a potential difference in speeds between the ingress and the egress ports. So what that means is basically if the data is coming too fast in the incoming port, which is the ingress port, the buffering can be used to make sure that it's not going to have any issues when the data is sent out the egress port, the exiting port. So buffering will do all that work to make sure that the data flows properly. So that's one of the key advantages of store and forward switching. In cut-through switching, it forwards the frame immediately after determining the destination MAC address. So fragment or frag-free method will check the destination and ensure that the frame is at least 64 bytes. And if it is less than 64 bytes, it will still eliminate the frame. But as soon as it realizes 64 bytes and knows the MAC address that the data needs to go to, should be forwarding to, and the switch will quickly forward that frame out. So in the concepts of cut-through switching, it is appropriate for switches needing latency to be less than 10 microseconds, for example. It does not check FCS, so it can propagate some errors. It may lead to bandwidth issues if the switch propagates too many errors. So if you have too many error frames are going through, cut-through switching is probably a bad idea. And it cannot support ports with differing speeds going from ingress to egress. So if you have, remember, one of the key features of store and forward switching is that it can mitigate issues where ingress speed and the egress speed doesn't match with each other. So in cut-through switching, there's no buffering, so it cannot do buffering between the ingress and the egress speeds, so it can't support ports with differing speeds. So those are the two types of switching. Switching domains. Collision domains. Switches eliminate collision domains and reduce congestion. When there is full duplex on the link, the collision domains are eliminated. However, when there is one or more devices in half duplex, there will now be a collision domain. There will now be contention for the bandwidth, and collisions are now possible. Most devices, including Cisco and Microsoft, use auto negotiation as the default settings for duplex and speed. Remember, in my previous lecture, I cover the concepts of auto negotiation and duplex and speed. So basically, most of the devices nowadays, not only Cisco and Microsoft, but also other devices, it has the auto negotiation on by default. So that will obviously avoid the collision domains by matching the duplex or the method as well as the speed between the device and the switching port. So in here on the right hand side, we have a PCA that is connected to port 1 of the switch 2. And in auto negotiation, what's going to happen is this PCA network interface card as well as the port on switch 2 going to auto negotiate whether they're going to go in full duplex or half duplex. And it will also negotiate what speed which they will be communicating. In this example, it has auto negotiate, it's going to be in full duplex, and they both going to be using 100 megabyte per second, even though the switch can support all the way up to 1000 megabyte per second, because the PCA doesn't have the ability to support that speed. So that's what the auto negotiation does. So you can basically simply connect to a switch port and it will automatically do the duplex configuration as well as the speeds. Broadcast domains. A broadcast domain extends across all layer 1 or layer 2 layer 2 devices on a LAN. Remember our OSI model from our previous lectures in the Introduction to Networks lecture series. So this is where those layers sometimes come into play. So in broadcast domain, when we look at the broadcast domain, it extends across both layer 1 and layer 2 devices on a LAN. That's a very important concept you understand. You need to understand, right? And only a layer 3 device, which is a router, will break the broadcast domain, also called a MAC broadcast domain. So it's very important that you understand this concept. So broadcast domain extend out to all layer 1 and layer 2 devices. However, a layer 3 device, which is a router, will break the broadcast domain. So the broadcast domain consists of all devices on the LAN that receive the broadcast traffic. When the layer 2 switch receives the broadcast it will flood it out all interfaces except for the ingress interface. Remember, incoming interface or the ingress interface will not be used for flooding out, because that is the interface that which the data is received. So the switch will only, the layer 2 switch will only send the packets out from all interfaces except the ingress interface. Too many broadcasts may cause congestion and poor network performance. And there is something also called broadcast storm. What that entails is basically you have a situation in your network where you have configured some kind of a network administrative configuration that result in a massive amount of broadcast packets being sent out, causing the entire network to either bog down or basically go out of service. So that's called a broadcast storm. I will demonstrate what it looked like on a lab in a different video. Increasing devices at layer 1 or layer 2 will cause the broadcast domain to expand. So if you keep increasing the number of devices at the layer 1 or layer 2 level, so for example, if you keep adding more and more switches and more devices in here, that's going to increase the broadcast domain, and it's going to expand the broadcast domain as there are no routers in between. Alleviated network congestion. Switches use the MAC address table or CAM table and full duplex to eliminate collisions and avoid congestion. Remember, if the switch understands which port is connected to what MAC address device, it knows that it doesn't need to flood every single egress or exiting port. It can basically send it to that specific port. So the features of the switch that alleviate congestion also include fast port speed. So depending on the model or type of switch that you have, you could have up to 100 gigabyte per second port speeds. And then fast internal switching. This uses fast internal bus or shared memory to improve performance. For example, older Cisco switches will have a lower memory sometimes, and the newer Cisco switches comes with much higher memory capacity. Large frame buffers. This allows temporary storage while processing large quantities of frames. Again, newer switches, newer models have more abilities with the frame buffering. And high port density. With this provide many ports for devices to be connected to a LAN with less cost. This provides also for more local traffic with less congestion. So you could, instead of having multiple different ports, you will have a large number of ports on a instead of having a multiple different switches connecting your network, you could have a single switch with many ports, high port density, so that it will be much better at alleviating the network congestion. Hierarchical network design. So in hierarchical network design, we use the method of designing a network by leveraging the hierarchical model, which also simplify the campus network design by allowing focus at different layers that build on each other. So that's the key feature here. So it leverages the hierarchical model also to simplify the campus network design by allowing focus at different layers that build on each other. The layers of the hierarchical model are divided into specific functions categorized as core, distribution, and access layers. So we have core layers, distribution layer, and access layer. This categorization provides for modular and flexible design with the ability to grow and scale the design without major modifications or reworks. And I will go into depth of these layers later in this lecture series. So if we look at them in a little bit more detail, the access layer is used to grant the user access to network applications and functions. In a campus network, the access layer generally incorporates switch LAN devices with ports that provide connectivity to workstations, IP phones, access points, and printers. In a WAN environment, the access layer for teleworkers or remote sites may provide access to corporate network across WAN technologies. The distribution layer aggregates the access layer switches, wiring closets, floors, or other physical domain by leveraging module or layer 3 switches. Similarly, a distribution layer may aggregate the WAN connections at the edge of the campus and provide policy-based connectivity. So this is a key thing that you should remember. Core layer, also referred to as the backbone, provide a high-speed backbone which is designed to switch packets as fast as possible. In most campus networks, the core layer has routing capabilities, and the most campus networks may use nowadays fiber optics or optical fiber cables within the core networks, while they may use other methods on the other layers. Because the core is critical for connectivity, it must provide high level of availability and adapt to changes quickly. It provides for dynamic scalability to accommodate growth and fast convergence in an event of a failure. So these are the 3 major definitions that you should remember for your exams and quizzes in this particular series. Next few slides, we will look at these layers such as access layer, distribution layer, and core layer in little bit more detail. So the first slide is going to be the access layer. So it describes the logical grouping of the switches that interconnect end devices such as PCs, printers, cameras, as I mentioned before. And it also the place where the devices that extend the network out one more level are attached. This includes such as IP phones, wireless access points, which both would extend the connectivity out one more layer from the actual campus access switch. So the access layer will have those switches, the access layer switches, and then when you have connected the IP phones and wireless access points, for example, it's extend one more layer beyond that point. Next, this is the distribution layer. So the distribution layer in the campus design has a unique role in which it acts as a services and control boundary between the access layer and the core layer. So that's a key feature you should remember. And the availability, fast path recovery, load balancing, and QoS are all important consideration at the distribution layer. So on an exam or a quiz, if somebody asks, if you were to implement the QoS, which is the best place in this particular layered model that you should be implementing it, that would be the distribution layer. So generally, high availability is provided through layer 3 redundant paths from distribution layer to the core, and either layer 2 or layer 3 redundant paths from the access layer to the distribution layer. So these are the key features of the distribution layer. Finally, the core layer, which is the backbone of your network. So the core layer, from design point of view, the campus core layer is the most simplest yet the most critical part of the network. So core layer, because it is the backbone of your network, it is very simple. However, it is the most critical part of your network. It provides a limited set of services and is designed to be highly available and requires 100% uptime. Those includes like the servers and other equipment within that. In large enterprises, the core of the network must operate as a non-stop, always available service. So such as, like I mentioned, like a server. So you need to make sure that your network, the core layer in this particular hierarchical network design, is highly available system that has almost or always 100% uptime. Even though it is very simple, it is the most critical layer of your network. So that brings us to the end of this lecture. Now I will go over a summary of what we have learned in this module. So we learn about frame forwarding. We learn about the ingress, which is the port, that is the data is being entered, and egress, which is the port where data will be exiting. And I told you a simple way of remembering this. Ingress like input, IN, therefore ingress, the input port, and exit, EX, therefore egress with the E is the exiting port. The switch build a MAC address table, also known as a CAM table, to forward frames on the LAN. The switch can use either the store and forward or cut through methods of switch forwarding. Make sure that you understand the difference between store and forward and cut through method, and what are the advantages and disadvantages of each one of them. We also learn about switching domains. We learn Ethernet ports in half duplex will be a part of a collision domain. Full duplex will eliminate collision domains. A switch will flood out all interfaces except the ingress port if the frame is a broadcast or if the unicast destination MAC address is unknown. So that's a key concept that you should know. It's not only going to flood out all ports because it is a it is a broadcast frame, but it will do the same thing even if it is unicast if the MAC address is not in the CAM table or the MAC address table. Broadcast domains may be broken up by a layer 3 device such as a router. And remember, if you add too many devices to your layer 2 or layer 1 level, you're going to create large broadcast domains. And if you have also, as I mentioned before, a misconfiguration or something going wrong in your network, you could create broadcast storms, which I will demonstrate in a later video. Switches extend broadcast domains but can eliminate collision domains and relieve congestion. So remember that. Switches do not break broadcast domains. Routers do. However, switches still can eliminate collision domains and relieve congestion. And you should also know about the issues with full duplex versus half duplex. Having mix matches in your network and what it can result in, like slowdown of your network or network congestion issues. And that is the end of this video. If you like these type of lectures, please make sure to thumbs up this video and subscribe to my channel. I will leave a link in the description for this lecture series, as well as the lecture series from my previous module, which is the Introduction to Networks modules, in the description of this video. If you have any questions or concerns, please don't hesitate to reach out to me. Until next time, all the best and good luck with your exam, and have a nice day.